Okay, good evening everybody. I have just decided that I would um, implement the shunting yard algorithm to use expressions and shunting yard is an algorithm that's relatively easy to do. It just says here that it doesn't reject all expressions, but that we can do in our bottom-up parser. Yeah, that's actually exactly what I'd like to avoid. Okay. Alright. So we have parse expression, which takes parse primary. Well, look ahead, is a binary operator whose precedence is greater than or equal to the precedence we started with. We advance to the next token. And that has to be a primary expression, right? It can't be a binary operator, and so that's right. Then we have another peak. We peak. Alright, if it is a binary operator whose presence is greater than the operations, or it's a right associative operator whose precedence is equal to the operators. So that means right associativity can be reached just by putting them higher in the precedence level. We do RHS equals parse expression RHS. So that means we have something in our RHS already. Oh. So we do that by assigning to RHS first. And doing the result next. So the result then is the LHS we have parsed in and the RHS. Okay, that looks simple. So this one here is precedence climbing. Yes. Can we, this would be interesting, so can we just implement the pseudocode? Let's see. What are you doing here? Go away, OBS. And I want the this one on the left hand side to stay open, so can't I put it always on top on that? Not on this one, on the Chrome thingy. So Google Chrome file, view, profile. Well, I can just copy this out and put it in the IDE, and then we can implement it. No worries. Maybe here. I take this one where I tried to do my own parsing thingy. Where's the detach editor? There we go. This goes here. I'm gonna paste the algorithm description in here. If it were there. Let's go back to Wikipedia. Precedence climbing operator precedence parser. So take that, copy that code, and let's implement this one. So let's go to MetaC parser, the C file, and let's go. We've already split into parse binary and parse unary, parse primary and parse unary, which I think though is the same anyways. Okay, we start when we want to parse a binary expression. We start with we have the left hand side over here, let me put it like this. We have the left hand side, and it also needs the minimum precedence. Prec. So we can unroll the stack properly. Now, we peek the token. Already do that. Then we say while it's a binary operator, while is binary operator, peak token type, and operator to precedence of operator to precedence of bin operator expression from token type peak token type is greater than or equal to min prec. We are just stupidly writing what they're transliterating the code. Then we accept the look ahead. Maybe I can do this will then be x sprite model is binary operator from type and we can do bin x from here, whatever we can do here as well. We can say x right equals this. I hope that the compiler is smart enough to optimize it, or once we have transliterated this algorithm, we can do the optimized version ourselves. Now, we advance to the next token. Okay, we say meta C parser match, and the match advances not a peak match, a regular match, advances the token by accepting it. Peak token type. We match that. Actually, one thing we also might want to do is to give our nodes a location. We shall do that later. We can do that after parsing, in fact, because the tokens themselves have a location, and as long as the lexer doesn't flush its token queue, when it does, it also flushes the location queue, because it's meant to work with a REPL, and the text that you used to lex may not be available. So having a location for that doesn't really make sense. At least not keeping it around on the lexer forever, because there are space constraints for these kinds of things. Anyways, we now advance to the next token. We already assigned the next token type. Right, we match it. Now we've eaten the token. A primary expression comes next, so we say result E1. Result E2, right, because E1 we already have, which is like the left. So we say result E1 equals left, and we have to allocate a new result here when it is a binary operator. One thing we can do is to say well, technically we can allocate. After that we can just get a expression pointer, expression RHS equals parser, C parser, parse primary expression, so like that. So we now parse the primary from the right hand side and then we start recursing, and we say while look ahead is somebody who is greater than. So this time it's strictly greater than. So while look ahead peak token equals meta c parser peak token self while, and well, we have to do we can do this with a peak token type as well. At some point we should probably have a helper function for this, but then we're gonna have while is binary operator peak token type and that's why we need the operator. Okay, I see. Well, we can do that. We already have it. The opt precedence exploit is greater than, not greater than or equal to, but greater than precedence of opt plus 1 if look ahead precedence is greater if look ahead precedence is greater. Greater than to precedence of bin x from token type of peak token type. Then we wanna do what? We do RHS we do parse plus bounded expression self RHS and min precedence is precedence of the op. Okay, so let's do op prec check precedence. Let us set that one up. This is UM30 of precedence is greater than that, and then op plus 1 if look ahead precedence is greater look ahead is greater than the ops, or it is a right associative 1. That is, so wait, so we wouldn't get into this. We wouldn't get into this. If the look ahead precedence was greater. So I just put in the op precedence plus 1. Operational precedence plus 1. And I have to assign that to RHS, which is fine. So this expands on the right hand side. Kind of like the other one does. And we never assign to op anymore. Which makes me wonder if this look ahead and this look ahead should be different things. Well, we'll see, I guess. What happens when we run this. And then at the last step we return result equals alloc new expression of x right. This uses colon equals, which might mean that it introduces a new name. Or that we need the old one. It might mean that this RHS is part of this, but this RHS stands for itself, but no, that doesn't make sense. Okay, we allocate a new expression result E1 equals left result E2 equals RHS return results. So, and all the rest of this stuff where we tried doing things goes away for now. Does this compile? I misspelled up precedence. Now it should be ready. Misspell it here again. What do we start with? I guess we'll put the 0 by default. Well, it compiled. Let's see what it does. And it works with 12 plus 12. 12 plus 12 plus 12 over 12. It does not work with well, that's not good. I guess we have to step through what's going on here. Let's say 2 times 4 plus 3. Oh, 3 times 4 plus 3. Okay. First of all, we look at what x right is. X right is an invalid value because we only assign x right after assigning the precedence. So that's our first bug. We have to assign x right first. So now, colon E, let's say 1 times 2 plus 3. Let's go here so we can step. I wonder how did I do stepping with the was it F11? There was a next instruction is F10, right? So let's step through that. Alright, x right is a multiplication expression, which means we are here where my cursor is. Then we match that multiplication expression, so we have eaten this now. We want to watch RHS. RHS right now points to complete garbage, but after we parse it as a primary, it should be an integer literal and it should be 2. So let's see if it is. Changed is an integer literal, and if we look at the value, it's the integer 2. That's good. We peek into another token. This time this token should be a plus. Peek token. It is a plus. The operator precedence says that plus does not go above the 1. So we should skip this while loop completely. Should skip this while loop. Oh, we don't. Yes, we did. So we didn't change RHS at all, which we shouldn't, because we want to do plus 3 as another invocation. Okay, we're done with this. We return the result to this. And then we return that result. So the issue is that nobody ever comes to pick up the plus 3. which we should have opened. So in parse expression, we have to do the peak after the primary, which we do. To say we want to parse a binary expression. But we have to do that after we return from parse binary expression as well. So let's hope I can fix that up. So it looks like we got the algorithm right. We just gotta plug it in properly. One thing we could do would be to have the meta C wrong min track for the precedence and simply fold the binary expression handling into here. This would be left. This would be main track. And then in C++ we would assign those default values so you can call parse expression without providing a left or a min precedence. But since we're not in C++, we can't do that. And that's where the while is coming in. That is where the while is coming in. Because we got a loop until the look ahead does no longer contain a binary operator. So that should work though, even with the old way of doing things that didn't have the look ahead when we pass this through. It looks like parse binary expression only needs to call parse primary. In the other cases, it can call parse binary. So this is the issue. This is the issue. We have to keep being in that while loop. Right here. Otherwise we don't fetch the binary operator. So now if we actually implement this correctly, we should at least see all of our expression. which we don't. Ooh, no. What happened? Left is null. How can left be null, like ever? How's the call stack look? So we call parse binary expression, and RHS is null. Well, RHS should be the result of parsing a primary expression. And that should have succeeded, but apparently didn't. So the peak token type is div, which means that now comes the question of which peak token type. Okay. We start when we do binary expression parsing. We ask for whether it is an operator. And it wouldn't be if we couldn't peek a token. So we have binary operator. We go in, we grab the token type, and then what? We pass a primary. We check if there's another operator after it. If the op precedence is greater than the ops. So if the op precedence is smaller or equal to, we do this. Otherwise, okay, this allocating a new expression is not within the while, but what is within the while is peaking at the next operator. Equals essentially this. So just copy this, paste it in, and maybe then we are done with expression parsing for the moment, until we go and try and optimize it. Alright, expression 12 plus 12, go. Well, now they are raised to the left. Well, I haven't put a diff as a precedent, I think. So this one should have factored like this. And yet it didn't. We may have done a mistake in assigning precedences. I can increase the precedence of multiplication as with regards to addition. And maybe now this would look different. I'll say A times B plus C. The B falls out. What the hell? So it can deal with this, but it can't deal with this. What's happening to the B? B is the LHS of the other one. And if I keep the thing differently, and I go say A plus B times C, I get A times C, let's say A times B times C plus D. So this didn't fix anything. I guess I can change these things just to see what happens if I do colon E 12 times 12 x plus D, and all the 12 drops out. This would imply that I got something wrong still. Because playing with these numbers should just mean that the order of stuff gets wonky, but it shouldn't mean that term should disappear. That should not be happening. So this only happens if it is a plus operation. So if I have a plus operation at the end of a times operation, so this is where, oh, I see. If I change this one, shall we bet that now we have 16 plus D? What? Alright. No, this definitely should be happening. What could have been happening is that it replaces the expression with 16 plus d, like that I would have understood. Although it should really replace the expression by this, right? So that means either Wikipedia is wrong or I am wrong at the moment where I'm at. I would give Wikipedia the benefit of a doubt and say that I wrote the implementation wrong. So let's see if we got it wrong or not. Well, we probably got it wrong. The question is just in what way did we get it wrong? Wrong. We know that there are cases where we lose an operator. And that presumably happens. So what's weird to me is that we're not seeing allocating another expression. Like we allocate a new expression right at the very end. Well, and when we do the parse primary expression. So okay, shall we do a 0 here, because I don't quite understand what would happen then. I guess nothing would. This wouldn't affect the way that we lose expressions. Alright, so what is the expression we are losing? We lose the right-hand side of multiplication expression. And rather, we get an addition expression. And that one doesn't come back. So A times B plus C times D plus E gives us A plus C plus E. And the C shouldn't have stayed. The C and the I shouldn't have stayed the A. It should have turned into the A times B. The A times B would have been created by doing this RHS. Okay, let's give this a special name now. Let's call this RHS O. And that's the one that we assign. And here we get a new one. But what about so we parse arch O in, but we don't replace it. No, actually I don't. Well, it seems to compile, but 12 plus 12, that should still work, times D. Now we lose the times D here as well. But that would only oh. Now we lose it all the time. So is that because we changed the precedence? Or yeah, because now we don't factor anything in, we just pass the primary and put that into the RHS, and that can't be it. So the first version that we wrote seems to this does not seem to actually introduce a new expression. It just seems to change the RHS for a past binary expression where the RHS is chained on, where the previous RHS is the new LHS in the expression that we're creating. Which would have the effect of opening like left parens. The question then is, why don't we see them? Why don't we see them? What I'm doing right now is really just hacking around, which I shouldn't be doing, actually. 12 plus 12 plus 12. That should, oh, even that doesn't work. Okay, Q. Colon Q. It seems like we are not entering this when we should, because when we say lower than or equal to, then we get them in the 12 plus 12 plus 12 case, right? Then we get in there, which we didn't get into before. So colon E 12 plus 12 plus 12 at least. All right, that works. So this part of the loop Oh. Oh. I see. This LHS does assign to this. And we only, that's why this is in parens. Now this makes sense. So we allocate a new expression. Which is the result. And then we assign left to the result. That makes a whole lot of sense. Now we shouldn't be losing terms anymore. Alright, and now with the change in precedence, now we get it. Yep, it observes the precedence the way it should. Sorta. Twelve plus 12 divided by 12. I would want this to be 12 divided by 12 times 12. I would want this to factor the other way. And the only way I can get it to factor the other way is if I change this. So if by default you have to factor to the left, and this is what happens if you do not go into this while loop, then you factor into the left, I believe. Plus 12 plus 12. Yes, now it factors left. Now it factors left. This is what it should do. This is great. So now expression parsing is basically done. Right? Great. And now we can have here the post-op. Like if we don't have, well, if we don't have if it's not a binary operator, so if is binary operator pick token type, then we do this whole shebang. Whoops. We have to go here, pull in another price, go like this to have our post precedence operation. This can go away. This can go away, and I believe we are done now. So, if I now say z equals d plus a plus plus, expression parsing, then this looks fine. I mean, it still doesn't parse the post increment, I don't think. So that has to go above the the binary operator parsing, because it would just determine that it's not a binary operator. Or is it because it calls parse primary? Well, at the very least, we now have, courtesy to Wikipedia, this algorithm, which I believe is precedence climbing, seems to work. It shall be good enough for me for now. So we have gotten precedence climbing to work without really understanding it, but what else, right? D divided by A times C. I'm not sure that that factored the way I would have expected it to factor. Well, it factored to the left, which it should. Alright, I'm just gonna keep it the way it is. For now, thank you for watching.